Right. So hello, everyone. Good morning. First, I would like to thank the organizers for the kind invitation, and it's a pleasure being here. So the work that I'll be presenting today was completed with my PhD advisor, Yariv Kafri. You will see him next week, along with our collaborator, Julien Tailleur, up until recently from Paris Diderot, and as of 3 weeks ago from MIT. So the work that I'll be presenting deals with the motion, the stochastic motion of a passive tracer particle in a bath of many active particles. And you could judge by the titles that I cover at least 2 of the 4 subjects, so definitely non-equilibrium. There's also anomalous transport. Unfortunately, no extreme value statistics or large deviations involved. Everything here will be typical. Right, so I really shouldn't be giving an introduction to active matter to this audience, especially after the few excellent introductions that we received this week. So let me just give you a reminder. So active particles are essentially particles that propel themselves by consuming energy. And the classical example is we think of something living as these run and tumble bacteria. This is essentially the same video as in Francesco's talk yesterday. But also in recent years, people have come up with experimental systems in which we can synthesize non-living active particles, such as these Janus colloids. So the fun thing about all of this is that we can use the same physics to describe both living and non-living things. Right, so a minimal model for an active particle, which basically encompasses most of the models that we've seen over the last few days, is the following overdamped Langevin equation. So we have here the velocity of the particle. It is given by a thermal white noise and external forcing. So this could be interactions or some external potential. And so far, this is just the equation of motion of a Brownian particle at equilibrium. What makes this thing active is the propulsion term. So there is some characteristic propulsion scale V, which propels this particle forward. And this V term has 2 important properties. It breaks time reversal symmetry, so generically the system does not reach an equilibrium state. And the other important property is the persistence time. So this particle randomizes its propulsion every now and then, stochastically through some mechanism. There are several studied mechanisms, such as the run and tumble particle that you can see here. And we have, by now, we are all experts on run and tumble particles. Because of the last few talks. And so on average, the particle randomizes its velocity, its propulsion velocity after this characteristic timescale tau. And along with the velocity scale, they define a persistence length, which would be the average characteristic distance traveled by a particle before randomizing its velocity. Now, on very short time scales and very short length scales, much shorter than the persistence time and length, the particle essentially never randomizes its velocity and travels in straight lines, ballistically. On very long time scales and length scales, much larger than the persistence time and length, the particle has randomized its velocity many times and essentially undergoes Brownian motion in the typical regime. So we have an effective diffusivity given by the velocity squared times the persistence time over the dimension. And we can also relate it to an effective temperature via the mobility coefficient. So, of course, yesterday we saw that in the non-typical regime, in the large deviation regime, this does not hold. But in the typical regime, essentially on long time scale, it just converges to Brownian motion, right? So, of course, we know that this is not the entire story. And the way to see this is through this extra term here, the external forcing. So one of the easiest way to see the non-equilibrium nature of active matter is simply throwing some asymmetric object into your active fluid. In this case, we will observe something which is known as Ratchet effects, which is just a term for the class of phenomena at which one can extract work out of fluctuations by breaking both a spatial symmetry and time reversal symmetry. And Ratchet effects have been studied for years, originally in the context of driven diffusive systems. But in active matter, you could obtain them generically almost everywhere. So there are a few famous experiments. For example, this ratchet wheel in a bath of E. coli bacteria. So you could see that the bacteria, because of the asymmetry of the wheel, they rotated persistently. Another famous experiment, again, E. coli bacteria, and now we have a semi-permeable partition. This entire thing is inside a box. And this partition is made of funnel-shaped barriers, which again have asymmetric shape. And we let the system evolve, and after some time, we see that the density gets rectified. On one side of the partition, it's much higher compared to the other side. And of course, these two effects are obviously non-equilibrium, because in an equilibrium system, both of these would violate the second law of thermodynamics. But of course, here we are far from equilibrium. Yes? Not persistently, not on average. So there would be fluctuations, but it cannot rotate on average. Otherwise, you could couple to this rotation and produce walk out of just one temperature bath, one heat bath. So this would violate the second law, essentially. And there's, of course, the famous Smolhovsky-Feynman ratchet, which is exactly deals with this problem. Right, so these are very clean experiments, but you could also do these at home. All you need is a glass, a piece of paper, and some honey, and you got a fly trap. So the paper cone directs the flies into the glass. And actually, fishermen also use a similar device. They have some form of net, conical net, and there's like a funnel, and fish would swim inside, but they will have a difficult time to get to the outside. Even though they can, the trap is fully open. And you could see why this is the case through the more clean setup here by Olivier Duchau's lab with the infamous hex bugs and a few pieces of Lego, that basically particles get stuck on one side of these obstacles and flow freely through the other. So we could really see the coupling with the persistence of these particles and how it leads to this rectification phenomenon. Right, so if we look at all of these phenomena, we can identify some global properties. So first of all, the density is a non-local function of the potential energy landscape. For example, here, there is the same potential energy on both sides of the partition, and yet we see very different densities. Right? Of course, a Boltzmann distribution would never look like this. The densities must equilibrate. Another thing we see is steady circulating currents, such as in this experiment. And in general, we see this positive net walk production, a pumping action. So a very simple way to think of these asymmetric obstacles in active media as just pumps in ordinary media. Okay? This analogy has been studied quite extensively. Right, so another manifestation of these effects occurs when we let one of these V-shaped objects to move freely in the fluid, okay, in which case I will refer to it as a tracer particle because we can trace its motion. So then if we prevent its orientation from changing, let's say using an external magnetic field, what we will observe is a persistent motion. It will be propelled forward at a constant velocity by a constant force. So here you see some numerics, and here you see an experiment done, and they control the orientation of this tracer particle with a magnetic field. They also rotate it every now and then just to play with it a bit, but basically the propulsion is solely due to the active bath. They do not propel it at all. Here, this is bacterial turbulence. So this is E. coli bacteria, very dense. This is not a setup that I will consider in my theory. I will consider a dilute setup. But again, we see the same effect. It's very generic. Okay, so but this is just the average motion. What about fluctuations? So Q us. So we derive the long-time dynamics of tracers in active bath. We focus on the long-time regime, and we do this in one dimension. So you could imagine a long, narrow channel filled by some viscous medium, and in the middle there is a large passive tracer surrounded by many small active particles. And we consider both the case of a tracer of arbitrary asymmetric shape and the somewhat singular case of a fully symmetric tracer. And the important thing that we find is that the long-time dynamics are heavily influenced by this asymmetry, by the change of symmetry. Not only on average, but also the fluctuations. That's what I would like to show you today. Right, so a bit of motivation. So I don't need to tell you about the importance of tracer particles that have been used in recent decades extensively in microrheology to measure experimentally properties of fluids and materials. But they are also used in a theoretical construct to construct observables that our theory could produce. And since the original discoveries of Einstein, Smoluchowski, Langevin over 100 years ago, we've came a long way. And by now, we pretty much understand the motion of tracer particles in equilibrium baths pretty well. However, the case for an active bath remains much less clear, even though there have been various studies on this problem for over 20 years. So here I list a very partial list of some papers that made significant progress, but there's like almost 100 papers on this subject in just 20 years. And really, if I had to pinpoint when the interest in this problem began, I would point towards this seminal experiment by Wu and Liebschaber from 2000. So what they did, they took a bunch of passive silica beads, they threw them into a bath of active E. coli bacteria. They then tracked the motion of the beads using a camera and extracted their mean square displacement. And this is what they got. They got on very short time scale ballistic or quadratic evolution with time, and on very long time scales, diffusive or linear evolution with time. And this came as a surprise to them at the time, since the system is highly overdamped, right? No inertia involved here. And so even though the term active particles wasn't even around at the time, they suggested to model the motion of these beads using the very same Langevin equation that I presented to you before, where the propulsion term is given by a colored noise, just exponentially correlated noise. So it's a rather simple exercise to start with an overdamped Langevin equation, some colored noise, derive the mean square displacement. This is what you get. And this indeed obeys the correct asymptotics at the two limits. And this has been the picture in the field for roughly the 20 years to follow. Namely that passive particles in active baths are equivalent to active particles in passive baths. And there are loads of studies on extension of this model. But what I want to stress here is that this picture must be incomplete. And one major reason for that is that active baths have a locally conserved quantity, the density, right? There's mass conservation, we have a continuity equation, and therefore there exists a slowly decaying hydrodynamic mode in the system, which prevents the existence of a single relaxation timescale, such as this tau. And it is known from equilibrium systems that in low dimensions, this fact leads to far-reaching consequences about the transport properties, and namely it leads to anomalous transport effects, and there are several experts here in the audience which have studied these issues. Right, so let me give you a quick introduction to this subject matter in the context of equilibrium system. And this will be somewhat complementary to the introduction we received yesterday. So yesterday we saw an introduction from the perspective of hydrodynamics, but this would be from the perspective of a tracer particle. Yeah. Yes, exactly. Yeah. And I will discuss this power law a bit more now. Yeah. So the textbook's picture of Brownian motion of a tracer particle would be just a simple Langevin equation. We have instantaneous viscous friction balanced by white noise. And of course, this equation is memoryless, and the noise has delta correlations, so it's not correlated with its past. And the central paradigm that we assumed in order to write down such an equation is a separation of timescales. We assume that the bath relaxation occurs on a timescale which is much shorter than the timescale it takes for the particle to relax. However, for baths with conserved quantities or also spontaneously broken continuous symmetries, this picture is incomplete, and we actually need to replace the equation with a generalized Langevin equation. So now we have retarded friction, and this gamma here is a memory function. And this memory function and the noise correlations now have power law long-time tails, as you said. And let me just give you all really, I mean, it might be very trivial to some of you, but again, I'll just present to you a really simple example for why we have these power laws. So let's consider our tracer particle in a bath, and let's consider a force carrier. In most cases, this would be a bath particle. So this bath particle hits the tracer at times t equals 0 and exerts a force, f of 0. Now, since the dynamics of the bath are conserving, they conserve mass, this particle cannot go anywhere. It will not be absorbed or it will not disappear. There won't be any new particles generated instead of him. So the only thing this particle can do is continue its motion through the solvent, presumably diffusive on long time scale, and perhaps return to the tracer at a later time, t. And hit it again and exert another force, f of t. The thing is, because the dynamics of the bath are conserving, there's always a finite probability to hit the tracer again at a later time that this particle will return. And in fact, we know from the solution of the diffusion equation, right, just the diffusion kernel, that this return probability, the probability to return to the tracer, will behave as a power law. And so the correlation between these two forces also has to be a power law. That's really the simplest picture. Okay, so I'll give you just a couple of examples, really well-known ones. So when there's a conservation of momentum, the tails decay as t to the minus d over 2. The dynamics are dominated by diffusion of momentum. And both tails decay like so. D is the dimension. However, somewhat less known, yes? It does not fail. It's also the case for a passive bath. No, so in fact, in water, if you have a tracer particle, there will be power laws. I will talk about it in a minute, but essentially the power laws decay sufficiently fast that we do not notice them on long time scales. This was discussed a bit yesterday in Anupam's talk, that we still can have the transport coefficient as long as the power laws decay sufficiently fast. But there will be power laws. Okay, so a somewhat less known result for baths that do not conserve momentum, so essentially baths of Brownian particles, just mass conservation. Well, sometimes it will be tempting to think that because we don't have momentum conservation, we won't have a power law, but again, mass conservation alone is sufficient for a power law. And the exponent is d over 2 plus 1. So it decays a bit faster because of we have one less conservation law. And this result was first proven by Hanna and co-workers in the 80s. The momentum conserving case was proven by Alder and Wainwright in 1967. So it's a pretty old result. They got it from numerics, and they were kind of surprised. They expected an exponential. Right, so what are the consequences of these? So if the tails decay sufficiently fast, that's relating to your question, Sanjeev, then not a lot. So if the exponent here is larger than 1, on long time scales, we can still define a finite noise intensity and a finite friction coefficient and define a finite, well-defined diffusivity. And if you track the motion of the particle, you just solve the generalized Langevin equation using a Laplace transform and take the long time limit, you will see that the MSD on long time scales evolves diffusively with this diffusivity. So on long time scales, we do not see a lot of difference from the memoryless or time separation, timescale separation picture. Things get more interesting when the tails decay too slow, when the exponent is either 1 or smaller. In this case, these integrals, these transport coefficients diverge, and the diffusivity is ill-defined. In this case, the MSD will will evolve non-linearly with time, and this is what we call anomalous diffusion. And anomalous diffusion has been studied for years. There are many examples for anomalous diffusion. We saw one example yesterday for superdiffusion. Another example is that for baths with conservation of momentum, since the tails decay as t to the minus d over 2, for d lower than 2, they decay too slow, and presumably they will give rise to superdiffusion. In fact, they lead to a breakdown of the simple hydrodynamic picture in low dimensions in one dimension, and things get more complicated, but still there are many systems that present superdiffusion with a different exponent though. For systems without mass conservation, the tails decay sufficiently fast in any dimension, right? You could inspect that even in one dimension, this decays sufficiently fast. And so we have normal diffusion in any dimension, and we can always resort to the simple Langevin equation on long time scales. We don't have to worry about these tails as long as we focus only on in the long time limit. Now, let me just give you a quick recap of all of the things I've said because it's somewhat dispersed. So active particles are particles that consume energy and propel themselves forward. They randomize their velocity every now and then. Ratchet effects in active matter are the rule, not the exception. It's very easy to obtain them. And the problem of passive tracers in active baths remains largely unsolved. And the aspect that I would like to focus on in this talk is the fact that we have long time tails in the active medium due to the conservation law. Specifically, and as I said, these long time tails can give rise to anomalous diffusion in low dimension. And what I will show you is that how ratchet effects not only modify the average properties of the tracer, but also the fluctuations in such a way that we will have anomalous transport. So we will have ratchet effect induced anomalous transport. So yeah, as I said, this will be important. This is basically recapping what I said. The long time tails will be important for the asymptotic dynamics of the tracer. And the crucial bit is that we have universal exponents which depend on the tracer symmetry. So there will be one exponent for this and one for this. Right, so we want a theory of tracers. So the first step is writing down a generalized Langevin equation. So I will write down an overdamped one, but you could also write down an underdamped one. So we have here a retarded friction due to the active bath, and a noisy force, again, due to the active bath. And this noisy force, because of the ratchet effect, can actually have a non-zero average if the tracer shape is asymmetric. On top of these, we have coupling with the ambient viscous medium. So just simple viscous friction and white noise. Basically, I neglect here the tails of the medium and focus only on those of the active bath. Now, to write down such an equation, again, the central assumption is an adiabatic or quasi-static limit, where the tracer motion is relatively slow. Otherwise, we will have higher order terms here in the velocity. So the question is then how to derive such an equation. There have been various approaches. For example, writing down a Caldera-Leggett type model and using non-equilibrium linear response theory by Christian Maes, and mode coupling theory by Thomas Voigtman. The approach that we took involves a technique which is known as Adiabatic perturbation theory. It was developed originally in quantum mechanics and then was transferred to Markov processes. But the effects that I will show you, you could derive with any approach that you would like, basically. So let me get more specific. Let's talk about the model. So we think of this quasi one-dimensional channel, and we want to model it with a one-dimensional model that we could actually solve analytically. So the important property that we see here is that particles can bypass each other and the tracer. So the model that we take is simply run and tumble particles on a line interacting with a potential that can move. So this potential represents the tracer. So specifically, the equations of motion are these. We have here the velocity of the tracer and that of the bath particle. They are related to the interaction force between the tracer and the bath particle. And we also have a propulsion term, just a telegraphic noise that by now we all know pretty well. So it just flips between plus and minus one stochastically with some rate. And here, for the analytics, I'm neglecting interactions between the bath particles, so they are non-interacting. For the numerics, we actually have also simulations with interactions, and the results are the same. So this is just for the analytics. So any questions before I continue? Perhaps. Been a very busy presentation. Okay, so we know the average properties of these equations. First of all, we know that in a steady state where the tracer is held fixed at a particular position, we will observe the so-called Ratchet rectification. Pretty much the same effect observed in this experiment, it will manifest in this setup. So the cool thing about run and tumble particles in one dimension is that we have an exact expression for the steady state distribution, for an arbitrary potential, and we could obtain expressions for the densities to the right and to the left of these tracers, and they would indeed be different from each other. And the force on the tracer, do you have any guess what it will turn out to be? Anyone has a guess? The average force on the tracer? It will just be the ideal gas law, simply the pressure difference between either sides of the tracer. So you could either use the ideal gas law, which is applicable for the system, or compute this exactly from the steady state distribution. And this means that on long time scales in the regime where the friction is very large, on average, the tracer will indeed move with a constant force. Yes? Yeah, that's the interaction force. This is derived from this potential. It's minus the derivative of this potential. And the average force is simply averaging this over the steady state distribution. Yes? No. No, so there is no thermalization, and the steady state is a very non-equilibrium one. This is a non-equilibrium steady state because of the rectification. There is an effective temperature scale. It appears as a scale. And there is also an added value of an equation of state. So although this is a non-equilibrium setup, a non-equilibrium steady state, there's still an equation of state with this effective temperature. And this is It is a non-trivial statement. There's a paper from 2015 which proves for which classes, I can direct it to this paper, which proves for which classes of active matter will you have an equation of state or not. It relates to whether there is interaction with the internal degree of freedom of the active particle. Here there is none, just an interaction potential, so there is an equation of state, even though the system is out of equilibrium. Yes, well, it depends, but yes. So what you will compute is the average of the force over the steady state distribution, and you will do this inside the tracer, but it will turn out to be exactly this density difference. I can show you the calculation perhaps later. Yes. Yes, I didn't mention it, but I assume here that the force is sufficiently small. It's smaller than the propulsive force, so that particles could climb over the tracer. Yes. So not with this potential. This potential is piecewise linear, and it will jump directly to the outside value. Yeah. So you're talking about some boundary layer forming next to the tracer, perhaps. So this will occur due to the interactions with the particles. So So I can observe it in either two cases. Either I let the potential here decay in some way and not jump straight from the force. I let it to decay in some way and not just jump from a finite force to zero. I will see this boundary layer. Or I allow for interparticle interactions. Then they just accumulate sort of, and if they are nearby each other, yes. But I will not consider this case here. If you have an aggregate of tracers, it's important, yes. It depends. So there can be either repulsion or attraction. Yes. Not necessarily. It depends where they are with respect to each other. So if they are sufficiently far away from each other, under some circumstances, there can be attraction. And there actually could be, they could lock into a finite distance from each other and move together. So this was shown in a previous paper. I can direct you to this paper by Yariv and a few others a few years ago. So it depends on the separation and the asymmetry of the tracer. Far away. Close to the tracer, there will be depletion-like effects. And so this could also be actually attraction in some cases. But here I will focus only on a single tracer. Okay, so we want to evaluate this equation. We need to have the coefficients here, right? We need to have the memory function and the noise correlations. So we obtain these using the adiabatic perturbation theory. And what it tells us basically is that the transport coefficients are related to correlations with respect to an ensemble at which the tracer is held fixed at a particular position. Yes? I just didn't draw it, but there is a density profile. Yes, yeah, there is. It's not repelling all the particles. There is some profile which looks, I can perhaps draw it if. So for the tracer that I drew over there, if that's the tracer, the profile will look something like that. It will jump in the points where the force jumps. Yeah. Okay, so we use adiabatic perturbation theory, and it tells us that the transport coefficients are related to correlations with respect to an ensemble at which the tracer is held fixed. So that's the adiabatic expansion. You expand with respect to a small velocity. So the noise, we take it as just simply the stochastic force that the tracer experiences if it is held fixed. And the memory function, it is given by this complicated formula. And here, rho s is the steady state distribution. It's the distribution of particles at a particular position x and orientation sigma. So we evaluate it like so with respect to the static ensemble. And then we have the equations, right? So the task is now to evaluate this. This is the crucial, hard technical task. So we did this. By the way, I didn't mention, quite trivially, if you put here a Boltzmann distribution, you obtain back the fluctuation dissipation theorem, right? Because this would be e to the beta, the potential. So we evaluate the correlation function of the noise and this complicated correlation function, which is the memory function. So first I will just present you the results, and then I will give you some heuristic derivations for them. Right, so for an asymmetric tracer, what we obtain that the long time tails decay as t to the power -1/2 in one dimension. And this is too slow. Okay, the exponent here is smaller than 1, and so we have anomalous transport. So on long time scales, the MSD evolves non-linearly with time. It evolves as t to the power 3/2. This is on top of the steady propulsion. So the tracer moves on average at a constant speed. And about this average trajectory, there is a super diffusive expansion of the fluctuations. Gamma t. Which gamma t are you talking about? This one. So the long time tail, the leading order contribution, does not change its sign. Yeah, large T limit does not change its sign. I will talk about the change of sign in a minute also for the symmetric tracer. So also the peculiar thing that we see is that when we tow the tracer at a constant velocity and measure the friction force due to the active bath over time, this friction force grows as time with the power to 1/2. And we actually have exact analytical expressions for these two coefficients here. You see here numerics, and on top of them, the analytical expressions without fitting parameters. So you could see they fit quite well. And the important thing about these coefficients is that we find that they are proportional to the average force on the tracer squared. And recall that this average force is non-zero only when the tracer shape is asymmetric. So when the tracer shape is symmetric, these leading order contributions vanish, and we lose the anomalous transport effect. We resort to the next order, which decays faster as t to the -3/2. So this is sufficiently fast, and we recover normal diffusion and a finite friction with some correction that decays as t to the -1/2. So, okay, here we do everything in one dimension, but essentially the 1/2 would be a d/2 in general dimension, and the 3/2 would be d/2 plus 1. So if we increase the dimensions, the tail decay faster, and that's why we can recover normal transport in higher dimensions. Right, so these exponents, -3/2 and this -1/2 are the same ones that you will have for a tracer in an equilibrium Brownian bath. So this is exactly the d/2 plus 1 I presented earlier. So seemingly nothing interesting here. However, as perhaps Christian suggested, we have a finite friction, but it actually could be negative. And indeed we find it to be negative in some regime. Namely, when the tracer size is on the order of the persistence length or smaller than it. In this case, the friction coefficient becomes negative. This is numerics and against analytics again. And actually, it is supported also by other numerics done by the Stark group in Berlin. So they did numerics for hard spheres, active hard spheres in 2 dimensions, and they got a reduction of the friction coefficient. And then I pointed out to them that it's because of that in their regime, the tracer is smaller than the persistence length. Simulations, yes. Yeah. So they simply measure the force on the tracer and divide by the velocity, and they average it over time. Yeah, you could measure also, you could tow at a constant force and measure a constant velocity. Not necessarily, but if I recall correctly, I think they did both ways, but I might be mistaken. So F is not a parameter. We have a formula for it in terms of the microscopic parameters. So as a function of the potential shape, because we have an exact expression for the steady state. So we know. Yes. Yeah, we haven't checked this numerically, but there should be a crossover between anomalous to normal. Yeah, you just compare the t to the -1/2 to the t to the -3/2. When they are comparable, you could get a time scale. We haven't done this, but you could do that. Yeah. Okay. Right, so this is neat. So again, let me summarize. We have superdiffusion and a friction force that grows with time for asymmetrically shaped tracers, and normal diffusion and finite friction, which can be negative for symmetric ones. And we have generic mechanisms, which I will now show you. So, yes. So here the dynamics are fully overdamped, so no mass involved. There should be a mass generation or mass reduction. So this was obtained using adiabatic perturbation theory for an equilibrium tracer, actually, that there is mass reduction. So yeah. So I would expect it to be the case also for an equilibrium bath, in fact. So in the 2016 paper that I cited, they get a negative mass correction for a particle in equilibrium bath using this method. We could discuss this more. Yes? So you could evaluate this time scale, right? We can do that on the board perhaps, and it will diverge as the tracer asymmetry gets smaller and smaller. So you will need to run your simulation or experiment longer in order to see this time scale. Yeah. Okay, so what I will do now, I will just give you the heuristics of these results. I will not do the actual full math. Yes, for run and tumble particles in one dimensions, yes. Yes, for arbitrary potentials. Okay, sure. For a fixed tracer, not a moving one, yeah. Yeah, and I'm expanding about this fixed state. This is the adiabatic perturbation theory. Yeah. Yes. Yeah. I mean, I think Francesco would say that it's good, but yes. Okay. Also Sanjib, right? You also relied on that fact. It's cheating. Okay. Right. So essentially, I can give you really a very general, just in one sentence. So given a Markov process, you can write down the Markov equation with the Markov generator, and you could write the solution as a spectral expansion with all the eigenfunctions. And then what you say is that the spectrum, you expand the eigenvalues and the eigenfunctions about a stationary state. And you get automatically that the leading order contribution to the probability has some kernel, some convolution with the past. And once you evaluate averages like the force on a tracer, you get this friction kernel, essentially. So it's essentially an expansion of the Markov generator with respect to the spectrum. You take a wide gap in the spectrum. Yes, the spectral gap is a small parameter. So essentially the velocity of the tracer, yes. Yes. Yeah, yeah. It becomes an expansion. It's like a Taylor expansion in the velocities, except that it's all non-local and convoluted. Yeah. Okay, so let me now give you heuristics of these results. So we need to evaluate these long time tails, right, for both cases. So first of all, we can expand these correlation functions in the position basis. So here we have summation over initial and final coordinates, both position and orientation, initial and final forces. We average with respect to the steady state distribution to observe a particle at some position and some orientation. And we have the propagator, the probability, the conditional probability to start here and end up here. And likewise, for the complicated correlation function that is in the expression for the memory kernel, we can also expand it in the position basis. It looks like that. And now it is clear that the task is actually evaluating the long time tails of the propagator. So that's what we do. So we'll give you just a very simple argument for these long time tails. So let's say we think of this propagator. It's the conditional probability to start at some time t equals 0, at some position and some orientation. So we have a delta function here at some position at time t equals 0. And now we let this particle evolve. And we know that on very long time scales, the motion of the particle is essentially diffusive. So on very long time scales, the probability density will expand at a diffusive rate. There will be a diffusive front, which scale is square root of t, and it will move at this rate, and the probability distribution would expand between this scale, b of t here, which I marked, which scale is square root of t. So it will be smeared over this distance. And now I could look at this distribution and I could choose a point, another point x, at which I will evaluate this propagator, which is very close to the original position that I started in. So very far away from this b of t. Here in this schematic diagram, everything seems close, but it will be very far away from it. So these two will be close to each other, x and x prime, and b of t will be very far away because we are looking at the long time limit. So locally here, the system has relaxed to a local steady state. But this steady state is a probability, right? Because this thing is normalized. It's not a density. So we need to normalize the steady state with respect to where this probability is supported. But the support is simply of length 2b, right? So we need to normalize this probability over a region of length 2b. So this would be, to a fast approximation, the probability density at late times. Now what we can do, we could say, okay, this is a very large region. B here is very large. So we can omit the tracer, which is much smaller than, in size than B, from this integration region. And then to leading order, we simply have the density to the right of the tracer times B of t, plus the density to the left of the tracer times B of t. And noting that B of t scaled as 1 over square root t leads to this long time tail that decays as 1 over square root of t with a coefficient which is just the steady state distribution. So this is something completely general. You could do this with any diffusive, long time diffusive system. And we actually have also a systematic expansion. You could do a systematic expansion of the generator of the equation of motion in Laplace space and obtain this long time tail with this coefficient, proportionality coefficient here of pi, and see also that the subleading contributions are t to the minus 3/2. So this is where the long time tails really comes from. Right now, any information about the shape of the tracer enters through this steady state distribution only. So you could verify that, for example, for a free Brownian particle, the coefficient here would be a constant. It occurs that when we have a potential, this coefficient is the steady state distribution. And you could generalize this formula for any diffusive system. We did this for this active system, but it's a general property. And the important part is that this proportionality coefficient is indeed the steady state distribution, and it does not depend on the initial coordinate. So it does not depend on x prime or sigma prime, the coordinate at which the particle started. So when I will plug this propagator, the long time tail of this propagator, to, so I take this propagator and I plug it into the force correlation, basically the correlation factorizes to 2 averages, right? Because we have just something times a steady state with respect to one coordinate, and something else times the steady state with respect to another. So what we obtain is that the force-force correlation is simply the average force on the tracers squared times this 1 over square root t long time tail. And this is an exact formula. And we could do the same exercise for the memory, and we get something which is a bit similar, again, with the average force on the tracers squared. Now, okay, and this, if we plug it in the generalized Langevin equation, we switch to Laplace space, we integrate to find the mean square displacement, we take the long time limit, we get this. We get the t to the power 3/2 growth, and 3/2 here is a universal exponent. It does not depend on any details of the tracer, and we have this exact formula for the coefficient. Likewise, we can also compute the friction force, which would be just the integral of the memory kernel given a constant velocity, towing velocity u. And integrating it, again, we get the t to the power 1/2 growth with, again, the same type of coefficient. And you could see that both coefficients are proportional to the average force squared, so that for a symmetric tracer, this will all go away. So this shows really that the ratchet effects or the ratchet force on the tracer causes not only a constant propulsion, but also a slower decay of the correlations, which leads to anomalous transport. Okay, this is just what I said, and the exponents are universal. So any questions before I switch to the symmetric case? Yes? Mm-hmm. Yes. So I assume a very large system. So there is the same density very far away from it. Yeah. Yeah, but you could also do the same thing with a periodic system, in which case it will change linearly because of diffusion outside of the tracer, so it won't be a constant. We did the same exercise. As long as the system is sufficiently large, it still works, even with a periodic system. Yeah, they become the same at, let's say, at the boundaries of the system. But it still works as long as the system is large. Okay, so for the symmetric tracer, I will first show you a simpler setup. I will show you a tracer in a Brownian bath, just the equilibrium exercise, and then I will show you the active one. So let's say we want to evaluate one of these correlation functions. Let's focus on the force autocorrelation. So this is the correlation between the force at time 0 at the steady state and the force at time t. Now, essentially, we need to say, given that we have a particle, well, I mean, to evaluate this correlation, we need to ask, given that we have a particle initially distributed according to the steady state, let's say somewhere over here, and it exerts some force, f of 0, what will be the force that it will exert at a later time t? So basically, we need to average over the force that this particle will exert at a later time t. So we need to sum the probability that it will return to this side times the force on this side, plus the probability to switch to the other side times the force at the other side. So basically, these two forces, since the tracer is symmetric, are the same in magnitude, just opposite signs. So basically, this correlation function will be proportional to the return probability, the probability to return to the same side, minus the probability to switch to the other side. That's what we need to evaluate. And now, just for the sake of the argument, let's take a very simple approach. We think of a Brownian particle, and let's take a limit where the potential is very weak, so that we just think of the simple diffusion kernel. We just plug in the diffusion kernel. So we evaluate it at 0, here it is, and we evaluate it on the other side of the tracer. The tracer size is LT, so we evaluate it at minus LT. Now we subtract the 2, and we take the long time limit, so we need to expand these exponentials in 1 over t, right? T is very large. So we could already see that the leading order contribution, the 1 over square root t, they cancel out. We lose them, and only the 1 over t to the power 3/2 survives, and this is it. Sorry. So this is where the minus 3/2 exponent basically comes from. It comes from this cancellation exactly here. And this you have for a Brownian bath, and the same you have also for an active bath. You could do the same exercise again. Okay, and then this leads to normal diffusion because the tail, again, decays sufficiently fast. Now, what's the difference between a Brownian bath and an active bath? So an active particle has two important differences in our context. First of all, in the steady state, they are polarized against external walls, right? We saw this in Sanjeev's talk, when in the classical active phase of harmonic potential, they all accumulate next to the walls and point towards the walls. So this is a general property of active particles because if a particle is at the wall, it will remain at the wall as long as it is pointing towards it. But as soon as it points another way, it will leave the wall. So particles next to the wall will be somewhat more polarized towards the wall. This will occur in the steady state. And so we start with, let's say, with a particle which is polarized against the tracer walls at the steady state. And now the other property that this particle has is that it's diffusive only on long time scales, On short ones, it moves ballistically. So now it has some initial data which tells it to point towards the tracer center. So initially, it will undergo a ballistic run of 1 persistence length on average. After this 1 persistence length has passed, it will lose information of its initial data, and on long time scales, it will just switch to diffusion about this point. So we could imagine something similar to a Gaussian centered about this shifted average. Again, this shift in the average comes from the initial data, just the fact that the particle is polarized in the steady state. So now we could ask, so in the case where the tracer size is much larger than the persistence length, this shifted Gaussian will still be on the same side of the tracer. The probability to return is still larger than the probability to switch, right? So the force correlation would be positive. However, when the tracer size is comparable to the persistence length or smaller, the particle actually switches to the other side during its initial ballistic run. And then on later times, our Gaussian is on the other side. So the probability to switch is actually larger than the probability to return, and the correlation becomes negative. This is the general feature that causes these negative correlations. You could work through the same exercise with the more complicated memory function, and from that you would obtain, upon integration, a negative friction coefficient. So basically what you need to imagine is that particles just switch to the other side of the tracer and push from the opposite side. So they enhance the tracer motion instead of resisting it. This is essentially the negative friction. Okay, so let's summarize. Asymmetric tracers, they exhibit anomalous transport. They undergo superdiffusion on top of their average propulsion. They experience a growing friction, a friction that grows with time, and we've identified those as Ratchet effects. Okay. Symmetric tracers undergo normal diffusion and experience a finite friction with the regular exponents that we encounter for Brownian baths. However, this finite friction can actually be negative, and also the noise correlations, they also can be negative at late times when the tracer size is comparable to the persistence length or smaller. And we have exact analytical expressions for the coefficients that you see here. Great agreement with simulations, both with and without interparticle interactions. And yeah, this is what I just said. And one can also think of generalizing this to higher dimensions in some way. So really the take-home message here is that Ratchet effects not only lead to net currents, they also lead to anomalous scaling of fluctuations. Thank you very much. I can take questions.